All right, we're going to continue our discussion today with complex numbers, and I want to get into some properties to start off of the argument. Before we get too into those properties, make sure you have your calculator in front of you because I'm going to go through some things on the calculator that you're going to need to be able to do. So get your calculator out so you can practice this with us. All right, first I want to talk about some properties of the argument. So if we want the argument of z times w, we can separate that as argument of z plus argument of w. So z and w are complex numbers. The argument of z divided by w we can separate as argument of z minus argument of w. And then the argument of z to the n we can write as n times the argument of z. And hopefully these look a little familiar to you because these are very similar to the log properties we had back in algebra. All right, so what are we going to use this for? Let's suppose z is equal to the square root of 2 cis theta. So notice this is in polar form. And I want you to find the modulus and the argument of 2z. So 2 is a constant, so we're just going to write that as 2 square root of 2 cis theta. And that's pretty easy to see. The modulus is just going to be the 2 radical 2. And the argument is just theta. How about for iz? Start by writing I as a polar number. That would be cis pi over 2, and think about the reason for that. The argument would just be 1 because it's I. And if it's just I, it's on the positive part of the imaginary axis. So the argument would be pi over 2. So we're going to put that together with z, which is the radical 2 cis theta. Bring the radical 2 to the front. And using our argument properties, we can write that as radical 2 times cis of pi over 2 plus theta. That's a rule for cis. The modulus is just square root of 2. The argument is pi over 2 plus theta. And the last one we had was 1 minus I times z. So let's convert 1 minus I to polar form. It's going to be in the fourth quadrant. And if we do inverse tangent of negative 1, we'll get negative pi over 4. The argument. What's the modulus for this? It's going to be square root of 2. If we put these two together with the z we were given earlier, multiply the coefficients together, root 2 times root 2 is 2, and then combine using cis properties for the argument. The modulus is 2, and the argument is negative pi over 4 plus theta. Okay, so if you haven't gotten your calculator out, go ahead and get it out. I want to talk about how you can work with complex numbers in your calculator. There's kind of some cool features that you've probably never seen before. First, I want to remind you or show you, it's probably been a while, but you have seen this before, e to the I theta, this is called Euler's number, and that's just cosine theta plus I sine theta. That's just cis of theta, where the modulus is 1, the argument is theta. It's actually on your info booklet. If you go back to the algebra section of your info booklet, you'll see that this formula is on there. So in your calculator, we can convert between polar and Cartesian formula, or polar and Cartesian version if they're complex numbers. Let me show you how to do that. Try typing in 2 cis of pi over 8. So let me go ahead and go to my art view here. Okay, remember I have the old version, so it might look a little different. Clear out what we have here. So actually we need to be on the home screen. So if we have 2 cis of pi over 8, that's just 2. Oh, before I do that, let me make sure I'm in make sure I'm in radian mode. Of course, we're working in radians here. 2 times the cosine of pi over 8 plus, now the I is the little key right above the periods, the second I, times sine pi over 8. And it's going to give me a decimal answer, but this is the Cartesian version of it. So we have 1.84 8 plus 0.7653i. So there it is in Cartesian form. Now, your calculator, if you go to the math menu and then go over to CPX, that stands for complex number. So that'll give you some different things. That'll give us the conjugate of the complex number. It'll tell you the real part, the imaginary part, and the argument, which is the angle. The absolute value is really the modulus, and it'll convert between rectangular, which is really Cartesian form, and polar form. So let's try converting 1 plus I into polar form. So let me go back to the home screen. Let me clear out what's there. I'm just going to type in 1 plus I. So this is rectangular or Cartesian form. So if we go to the math menu, over to CPX, and go down to polar, the number already has to be in there, so it's going to convert it to polar, and there it is. So look at what this is giving us, 1.414, and it's e, I got e, to the I theta. So the theta is that 0.7853 number times I. And remember, what did we say that was? E to the I theta is cis of theta. So here's that same example. So we've got 1 plus I, and it gave me this approximately in the calculator. So knowing Euler's formula, that's really this. 1.414 is approximately square root of 2, and 0.7854 is approximately pi over 4. All right, so play around your calculator a bit, get used to some of those features. They can be kind of helpful. A little information for you here about Demoivre. He was a French mathematician, and I think he's probably most famous in math for his work with complex number, and particularly he came up with this thing called Demoivres Theorem. So let's talk about what that says. Demoivre's theorem is used to find powers of complex numbers when they're in polar form. So write this down. You're going to need to know this. I think this is in your info booklet, but you're going to know it pretty well after doing a few problems. So if we have a number in polar form, a complex number, and it's modulus times cis theta raised to a power n, we can break that down as the modulus to the n times cis of n theta. So this is why working with polar form of these numbers is useful, because this theorem only applies if you're dealing with the form in polar instead of Cartesian. Here's an example. Find the exact value of square root of 3 plus I to the 8th power using Demoivre's theorem. Okay, so let's convert this to polar form first. So the modulus is just going to be the square root of radical 3 squared plus 1 squared, which is just 2. And this will be in the first quadrant. So if we make a little sketch of it, where the real part is square root of 3, the imaginary part is 1, think about tan theta is 1 over the square root of 3. Where does tangent equal 1 over radical 3, or root 3 over 3? Pi over 6. So here's the polar form of the number, 2 cis pi over 6. So the theorem says we want to raise this to the 8th power. We're just going to take the modulus raised to the 8th power times cis of n theta, but n is 8, so that's just 8 pi over 6. If we simplify that, 2 to the 8th is 256. 8 pi over 6 reduces to 4 pi over 3. Now, if we started in Cartesian form, then we need to finish in Cartesian form. So let's go back and expand this back to Cartesian form. Remember, cis 4 pi over 3 is really cosine 4 pi over 3 plus I sine 4 pi over 3. That expands to this. Distribute 256, we get this. And that's Demoivre's theorem. And so tomorrow we're going to talk about, in the PowerPoint, how to apply this to solve equations.